So let's see if we can construct a Turing machine that accepts the language of palindromes. In metacode, we might proceed as follows. Find the first symbol, go to the end and compare the first symbol to the last symbol. If they're the same, delete the first and last and return to step 1. If not, crash. And remember, once you've said something, you're never allowed to change your mind or rethink your beliefs under any conditions, no matter what you learn or what new information comes your way. Oh, wait, no, that's politics. Remember, you can figure things out as you go along. So, somehow we want to reach the halt state, but we can leave that a little bit vague for right now until we get more of a handle on the rest of it. So now remember that in general, each move of our Turing machine will change the state, possibly to the same state we started with, change the symbol at the tape head, possibly to the same symbol, and then move right, left, or stay in place. So remember, concrete never hurts. So let's see if we can build a Turing machine that accepts the palindrome A, B, B, A. So remember, we'll prepend our string with a blank, and we'll see why this is important. We're in initial state Q0, and the symbol read is blank. We don't want to change symbols, and again we'll see why, and we'll move right. And since we haven't really done anything but get ready to read the first symbol, we'll stay in state Q0. There's a useful simplification we could make at this point. If the string is a palindrome, the first symbol will be deleted. If the string is not a palindrome, we'll know when we get to the last symbol, and our Turing machine will crash, so it doesn't actually make a difference if we delete the first symbol. So if we delete the first symbol at the start, we can avoid having to go back and delete it later. Now, in order to compare the first symbol to the last, we need to store it, but the only memory available is the internal state of the machine. So we'll need a set of states corresponding to the first symbol. So let QA be the state of the machine if the first symbol is A, and similarly for the other symbols. So we'll read the symbol, delete it, change the state, and move right. At this point, we're just looking for the last symbol, so it doesn't matter what the symbol read is, we'll keep the symbol, keep the state, and move right until we get to the end. But how does the Turing machine know we're at the end? Since the Turing machine can only read one symbol at a time, it only knows it's at the end if it reads a blank symbol. And so when we read the blank symbol, we have to move left. But note that we can't stay in the state QA since that state always has us moving right. So we need to change the symbol to a new state QD, which might delete the last symbol. Now, in this case, since the last symbol is the same as the first, we delete it, except the memory of that first symbol has been erased. Remember, the only storage we have is the state of the machine, and all QD tells us is that we are ready to delete a symbol. So we need a delete state that's specific to that initial symbol, and so we'll call it QDA. So this QDA stores the fact that the first symbol was A, and if the last symbol is also A, we can delete it. And in this case it is, so we can delete the last symbol. And now we want to move to the beginning. The important thing to realize here is we can't stay in the state QDA, because if we stay in the state QDA, we might end up deleting other symbols. So let's switch to a new state QL, which indicates we're moving left to seek out the beginning of the string. So we'll move left until we're at the beginning. And again, the only way we know that we're at the beginning is when we read a blank space. And this is why we need to prepend that blank space. Otherwise, the Turing machine would try to read past the start of the tape. Now, once we get to that blank space, we need to change states, and then move right. Notice that after the deletion, we essentially have a string that might or might not be a palindrome. So we might as well reset to our state Q naught. And now we're back where we started. Now notice that if we continue to run as we think we should, we delete everything and return to Q naught with the empty string. And since ABBA is a palindrome, then we want to enter the halt state. Or do we? As written, if we're in state Q naught and read the blank symbol, we'd go into the halt state. But that would also mean that when we started, we would automatically go into the halt state, and this would accept any string as a palindrome. This means we need a way to distinguish between the prepended blank space and a blank obtained because a symbol was erased. To do that, we'll need to enter a different state at the beginning. So we'll read that initial blank, move, and change to state Q1, then delete first and last, and now we're in Q1 reading a blank, and that'll take us into the halt state. And this suggests we need the following states. The initial state Q0, state Q1 corresponding to the imminent reading of the initial symbol, states QA, QB, and so on corresponding to whatever the initial symbol is, states QDA, QDB, and so on corresponding to the imminent deletion of the terminal symbol, and state QL corresponding to moving back to the beginning. So the moves we want, from our initial state Q0 and initial symbol blank, we want to switch into state Q1, ready to read the next symbol. We'll reprint the blank, but we'll move right. And so this prepares us to read the initial symbol. Next, we'll read the initial symbol, change the state, and move right. So the initial symbol might be an A, in which case we go to state QA, print blank, erasing the symbol, and move right. Likewise, if we read a B, but if there's no symbol present, then we paired off all the symbols and have a palindrome, so we should enter the halt state. Now if we're in either QA or QB, then as long as there's a symbol present, we'll stay in the current state, reprint the current symbol, and keep moving right. So if we're in QA and read an A, then we stay in QA, reprint the A, and move right. And if we read a B, we'll reprint the B and move right. And likewise, if we're in states QB, but if we encounter a blank, we need to change state, preparing to delete the symbols if they match, and move left. So if we're in state QA and encounter that blank, we get ready to delete the last symbol if it's an A, we print the blank, and move left. And likewise if we're in state QB. This should take us to the last symbol. So if it's the same as the first, we delete it. We'll also change state so we can move to the beginning and move left. So if we're in state QDA and we read an A, then the first and last symbols are the same. So we'll switch to state QL so we start to move left. We print a blank, deleting the current symbol, and move left. And likewise if we're in state QDB and read a B. Otherwise, we crash. And we can either define a rejection state HR, or we can leave the move undefined. We'll leave it undefined. Now, state QL should move us back to the beginning. So no matter what we read, whether it's an A or a B, we should reprint and move left. And the only time we change is if we read a blank space. And if we read a blank, we should change back into our ready to read the next symbol state Q1, and then move right. And so our TM for the language of palindromes has moves. Or does it? So let's check that these moves accept all palindromes and reject all non-palindromes.